So in the last few weeks, we started to talk about how to use Lagrangian to write down the equation of motion for one particle, two particles, or three particles. So the idea is simple, but you can see the math get very complicated once we have more than two or three particles. And because what happened is once you have more particles, there will be more degrees of freedoms, and there will be more variables to solve, so you will have a lot of equations. To deal with a complicated, complex system, it usually takes like a different, tools to do that. However, out of all these complex systems, there is one kind of special kind of system that is actually doable, that is called rigid body. Rigid body is a system where, like a pair, like you can see what I'm drawing here, it's like a pair. And let's say in the pair, rigid body meaning all the particles in the pair, the distance between them remain the same as it moves. If we impose that constraint, the degrees of freedom that we really need to describe this whole system is 3 translational degree of freedom. And that is naively, you can think about that, describe the translational motion for center of mass. However, but the pair can rotate. It can be rotating this way, it can be rotating that way. So there is also a 3-dimension that this pair, this rigid body can rotate to. So we also need 3 degrees of freedom to describe its rotation about the center of mass. So totally, we only have 6 degrees of freedom. The math, you will see it's still pretty ugly, but it becomes doable because this translational one is usually very simple. So you only need to do 3 equations. Let's go ahead and analyze definition of the physics quantities for rigid body. All right, so now let's start by setting up the coordinate. So let's say I choose XYZ as my coordinate. This is my space frame, like it's a frame that it's either not moving or moving with a constant velocity. I'm going to use big R to describe the position of center of mass. So this point is center of mass. And then for arbitrary point in my rigid body, its a position, I'm gonna call it RS, looking at the position in the space frame. All right, and then there is also another convenient position that we will want to know is the position of, say, this ith particles respect to the center of mass. So I'm gonna call it Ri. So this is notation I'm gonna use. It might be different than the textbook, but I will use this throughout the class. So now this is how I describe the position of each particle in my system, no matter it is in the space frame or in the center of mass frame. Now, after that, let's talk about the force, momentum, angular momentum, and the energy. The force, the total force acting on this rigid body is simply external force. Because the internal forces here, they will kind of cancel out each other because of Newton's third law. This you have already proved that in your pre-class quiz 1. The total momentum of the system is the same as the momentum for center of mass. Total angular momentum, turns out, of course, you can do the R cross P for each of them. Then you can try to massage your equations, organize your vectors. Then eventually you will find out that the total angular momentum equals to the angular momentum of the center of mass plus the angular momentum about the center of mass. The orbital one plus the spin one. Center of mass rotation can be defined as R cross P for center of mass. This would be R cross P, but all about the center of mass. Similarly, total kinetic energy also proved that in the homework 5, that it can be break into the kinetic energy of the center of the mass plus the kinetic energy about the center of the mass. So it's very similar to this angular momentum. The potential energy is essentially, you just need to count for the external potential energy. Potential energy depends on R. And since all the distance between the particles are the same in size, so there's no the internal energy will just give you a fixed constant. So I can always, reset my constant. That constant will not affect my physics. So this is how I should think about my physics quantities in a rigid body. Okay, so out of all of this internal angular momentum and this internal kinetic energy, these two can be written in a better format. Now let's take a look at this internal angular momentum. Internal angular momentum is R cross P, but respect to the center of mass. The P is mv. So I can break this down to m times v. So this is really R cross v with the m, which is a constant. And that v can be rewritten as omega cross r. So if I rewrite this equation, I'll get that. And this one, you can prove that this is essentially can be written as this. So that means my angular momentum will be a vector, and each component will be a linear combination of some omega 1 plus some omega 2 plus some omega 3. A very similar format will show up for the kinetic energy. So this two term is a more generalized equation. When you're taking 116, you probably see I omega for this one. And you probably see that kinetic energy, you will take the form of 1/2 I omega squared, right? So this is because in 113, usually the problem already chooses a very nice coordinate so that this tensor turn out to be diagonalized, so you can actually rewrite it in this way. But that's not always the case. The format here that I present you is a more generalized format.